Welcome to the session. Speaker is Nicole Migo from University of Bremen. Nicole has done foundational work in online algorithms, approximation algorithms, a lot of nice work in scheduling algorithms. And today she will talk about graph problems with predictions.
Thank you, Amit. Yeah, first of all, I want to thank the organizers for setting up this very nice workshop. I will talk about some recent work, which is also in the line of research in the area of learning augmented algorithms. So I mainly will talk about graph problems, routing and network design problems in a model where we use predictions to improve algorithms. So here, in the main part, I present some joint work with other people, mainly also with my PhD student, Alex Lindermeyer. Before I start diving into learning augmented world, let me start a bit more generally. So we're here in this workshop on algorithms and uncertainty, and we would like to solve problems even so there's input uncertainty in some manner. And of course, there are many different ways of modeling input uncertainty, right? So the two classical major streams would be online information, where we are lacking input data and it is revealed in some way incrementally. And in the stochastic information world, well, there's some probabilistic information. So we're given distributions or parts of the distributions. And the classic areas for solving problems for optimization under such uncertainty would be online optimization or stochastic optimization, or robust optimization is also somewhere there. And in the recent years, or maybe not so recent anymore, there has been a big trend in trying to adapt models, look at more practical models, trying to go beyond worst case scenarios. And this has been done in the traditional frameworks by adapting them, but there are also new frameworks like explorable uncertainty. For those that were here yesterday, I tried to advertise this a bit. And the big recent line of research on using predictions, which might be correct, but which also might be wrong. So using error-prone predictions in order to improve algorithms. And this is what I will talk here about. And we had already some nice introductions today by Ravi and yesterday by Ali, so I keep this rather short. So in very short words, well, we design algorithms. They have to live with the uncertainty, that's how it is. But in real life, we often have some additional information. Applications are often data-driven, so we collect data all the time, and we're very powerful machine learning tools that can come up with predictions about the uncertain input. And we should make use of this. Now, the problem is that these machine learned predictions, or let it be other kind of predictions, we cannot fully trust them. They might be correct, and in many, many cases, they are very good. They really predict the input, but they also might be completely wrong. And for us as the algorithm designers who want hard guarantees on the performance of algorithms, this is a problem, right? How can we make use of this? So there's this new framework in which we try to design algorithms that have some error-dependent nice guarantees. And the properties that we want are of the form that we want the consistency, which means that an algorithm that makes use of predictions, if they are very good, then our algorithm also should perform much better than an algorithm without this additional information would perform in a worst case. Yeah, so if I show this on this little picture here, so let's say here, this should indicate increasing error, and here's a worst case performance. Some traditional algorithm would have some worst case performance independent of the error because it doesn't make use of predictions. But our algorithm, or the ones that we design, should have a much better performance if the prediction is very good. But at the same time, it should be robust. So if the prediction is very bad, then there should be some bounded worst case still. And it ideally should not be too much worse than of an algorithm that does not use predictions. And ideally, we have some nice error dependency until the robustness kicks in. Okay, that's the goal. And this is a line of research that got pushed a lot by, 4 years back by Likoris-Wasylewicki and Kraska et al. But already earlier papers kind of had this flavor. but since those papers, this became a really vibrant research area, and yeah, every month, every week, new papers come out, so it's even a bit hard to keep track of this. So at a workshop in May this year in Switzerland, my PhD student and I decided the community wants some collection, some pool of, or some way of keeping track of literature that's coming up. So we, together with the community, collect recent papers there. So if you want to get into this field, maybe it's a good idea to look at this and get some feeling for what is known already. Going beyond worst case can refer to many different fields, right? Here in this talk, I will talk about online algorithms and competitive analysis. I try to go beyond rigorous, worst case bounds using those predictions. But of course, you could apply this idea to other problems or other performance measures, right? Try to improve running times, try to improve in mechanism design, price of anarchy, or in dynamic algorithms, the update time, whatever. Okay, but here we stick to online algorithms. And I want to talk about graph problems mainly. So here are two examples. Very classic problem is the Steiner tree problem as an online metric request problem. So here we are given the metric space, and then terminals appear one by one. So there appears a terminal, and at any moment in time when a new terminal appears, I must ensure that all the given terminals are connected. Yeah, so here the green ones are my requests, and here I connect them maybe directly. And overall, I want to minimize the total connection cost. And then appears a new request, and I have to connect it, and I continue. It could look greedily like this. However, if you look at the request that in the end appeared, I could have found a much cheaper way of connecting by taking this red line here, right? But I didn't know in advance. So I will make mistakes because of this online arrival of requests. And indeed, there are strong impossibility results, strong lower bounds. In this case of log n, also for Steiner forest, and also for online facility location, there are known strong lower bounds. Okay, we would like to overcome them by using predictions. So these are online metric request problems where requests appear in a list, so one by one. And there are other models where some timing issue comes in. So where requests appear online over time. So they have some scheduling flavor then automatically. So a typical example would be an online TSP version. So you all know the offline TSP problem, I guess. Points in a metric space appear, and you want to find a tour through all these points of minimum total distance. Now here, imagine time comes in. So let's say here's the origin, you have a server, the server moves at unit speed, and we get requests, we have to serve these requests, meaning we have to visit these points, and we compute an optimum tour. Or later, if you care about running time, then let's say you compute an approximately optimal tour. And now, let's say the server starts moving, but now over time, as time passes by, a new request might appear. And now we have to think about, do we incorporate it directly? Then another request might appear and so on. Or another alternative would be to say, well, I serve a tour that I computed. I ignore everything that appears in between. And once I'm back, I can compute a new tour on what appeared in between and connect those, right? So these are different, already different algorithms. They're actually not so bad. These are algorithms which are also used in practice often. And it turns out if we do our competitive analysis, so compare the performance of the algorithm with the offline performance of an optimal algorithm that knows all the requests in advance, then these two algorithms, they only have a competitive ratio of 2.5. So this is constant. It's a small constant. We're happy, actually. And one can show that with some smart delay strategy, one can even improve on this. I don't want to show this in detail here, but it's nice to know, though, that the best possible algorithm for this online TSP problem of this form is 2. Now, we could say we're done. So in the previous type of problems, we had non-constant lower bounds. It looks very difficult. We want to improve on this. And here, we have small constants. Why would we care? Well, a practitioner cares, right? If you go to a practitioner, to some delivery service who gets these calls, these requests for pizza delivery or whatever, this person would be unhappy if we guarantee, well, you get a good tour, you're off by, let's say, 100% at most. This is not nice because a practitioner might say, well, I collect all this data, I know roughly what's going on. I have additional information. How do we make use of this? Okay, and that's why also those small competitive bounds we would like to improve upon. So for such timing problems, so TSP-like problems, there are also generalizations like online dial-a-write problems where you transport, so a request consists of 2 points, and you have to move from one point to the other point to serve a request. Okay, and also there are small constant bounds are known. So now what I want to do is, I want to maybe mainly first talk about this online TSP problem, and I want to show you what could you predict, what's a prediction model, and then mainly I propose an error measure. So the main focus of my talk actually will be on discussing error measures. I hope to convince you that we present a quite universal error measure, which one can use for online TSP, for online dial-a-write, and also these other graph problems. Yeah. And then I will discuss a bit more about error measures and my view on error measures, and maybe we get time to have a glimpse also on some scheduling problem. Okay? But first, let's stick to graph problems, and I should mention that there's other work on our graph problems, actually on exactly this network design problem, this Steiner tree and facility location and so on. Yossi and Debmalia, they worked on this, and also other people. There's also work on graph exploration, but this has a very different flavor. And also work on minimum spanning tree problems where you can make queries for precise values. Okay, but this is something we ignore here. Really, for now, I would like you to have in mind this online TSP problem. Requests appear over time, and we have some additional information, some prediction. Now, what could be a prediction? Let me be very generous and let me say we predict the entire input instance. Yeah, so the whole request sequence, meaning requests with release date and points in the metric space, they are all given in advance. Now, they could be wrong, right? What could go wrong? Well, the location, so the placement, the point could be wrong. The release date could be wrong. It could even be that the length of the sequences is very off, right? So maybe the prediction says there are 3 requests, but actually 5 million requests appear. So this is very difficult to handle somehow. Here are some ideas for how could I measure the error. Well, one idea is to say, well, I could just count how many predictions are wrong. So how many of these requests, individual requests, are wrong. That's one way of measuring. And another measure is, let me say this here only on a high level, is that we try to match predicted and true requests. So in the metric space, we can just compute a matching. But if the length of the sequences is different, then I also allow some outliers, right? Some of these guys cannot be matched. So I've kind of 2 parameters. And none of these, I can really easily incorporate time. So if I look at this TSP problem, when requests arrive over time, this gets a bit more tricky. Yeah, and this is what we want to look at. We would like to get some error measure that also captures timing and maybe captures nice features of these suggested previous error measures. So maybe first of all, we should think about why do we want an error measure? Well, I would like to quantify how much wrong is my prediction, right? Because later I want a performance guarantee depending on this error. And this error should distinguish between good and bad predictions. But what means good and bad? Well, something can be bad for a reasonable algorithm, whatever a reasonable algorithm is. If I want to make use of predictions, I should trust them to some extent. So maybe it would be a good baseline to say a reasonable algorithm is a good algorithm for using these predictions and assuming that they are correct. Yeah, because any algorithm that wants to beat traditional online algorithms, it needs to make use of the predictions to some extent. Otherwise, it cannot improve. So what I want to, or the path that we follow here is, we would like to quantify how much does it cost a reasonable algorithm that trusts the prediction if these predictions are wrong. Yeah, how much does it cost? And now measured in the actual objective function. So in my online TSP problem, the total time for serving everything. So the make, spin, and scheduling notion. This is what my objective function value is, right? So I would like to measure in terms of tour length or total time, I would like to measure the error. One thing is very important, my error measure should, of course, be independent of any algorithm. Yeah. So now here's the intuition for our error measure, which we call a cover error. And we distinguish two types of wrong requests. We say they are unexpected requests. They were not predicted and they suddenly pop up. And there are requests that were predicted, but they were wrong. Yeah, so we distinguish these two. Let's look first at these unexpected requests. So here's my color code. Requests are green points and predictions are pink points. So let's say here's the origin where the server sits in the beginning. And here is only one predicted request. And here is an unexpected true request. How should I measure the error of this request? I could charge the whole distance to the origin, right? And say this is the error. But this is overestimating this too much because any reasonable algorithm has to serve or at least consider serving this predicted request. So then it would be somewhere in this area anyways, or at least at some point the server would go there, maybe it then turns around and travels back. But I could charge the cost for this unexpected request, I could charge this somehow to this predicted request. And it's very natural to look at the distance on the one hand, and also look at the difference in the release dates. No, because if my unexpected request appears much, much later, there's this gap in the release dates, and this is an additional waiting time, or in this time, my server could have traveled back. I don't care what it does, but there is some gap between the release dates, and this is something I also want to charge. So we can say that the cost for this unexpected request with respect to this predicted request is exactly the summation of these two values, the gap in the release dates and the distance between these 2 points. Now you could say, well, yeah, but there are many options, right? Who should cover an unexpected request? There might be many predicted requests. Well, let's look at all of them. Let's set up a bipartite graph. On the left-hand side, I have all these unexpected requests. On the right-hand side, I have all the predicted requests that could cover the left-hand side. And what I ask for is a min-cost cover of all these unexpected requests. And originally, you could imagine there's a complete bipartite graph, and I can exactly write the edge cost according to this function here, give each edge the cost, and then I want the min-cost edge cover. So here, it's very immediate to compute, right? I just take the cheapest connection and there's nothing really to do, but I would like you to see this bipartite graph because I later will generalize this, okay? So this is the min-cost edge cover for the unexpected requests. And similarly, I have predicted requests which don't show up. They are wrong. And I want to quantify what's their error. Well, I have a similar bipartite graph. On the left-hand side, I have these absent predicted requests. And on the right-hand side, I have true requests. And I want to cover all those on the left-hand side by any of those on the right-hand side. Okay? So there's not a matching or anything. So here, for example, this predicted request can cover several unexpected requests. Yeah? Yeah? Yeah. Not predicted. So these are the true requests, those that are really appear. So I want to charge the error of the absent predicted ones to those that truly appear. Because those I have to, so the same intuition, I have to serve them anyways, so I can also charge the detour, the cheapest detour to serve such an absent predicted request. And now my total error of an instance, so now I get a predicted instance, I get a true instance, I can compute these two types of errors, and I look at the summation, and this is now my cover error. This is how I measure the error of a given instance, okay? Okay, we can define this, let's keep it there. Now let's think about an algorithm, and then I want to show how we can make use of such an error in analyzing an algorithm. Okay, so let's take this given now. So we want to design an algorithm that makes use of predictions. Well, I would like to follow my predictions. Yes, there's a question?
How do we identify whether a given request is unexpected request or not?
So in hindsight, right? So I see this predicted instance, and in hindsight, I mean, I see what the actual instance was. And then I compute how wrong, so then I compute the error. How bad or how wrong was the predicted request sequence with
So
respect to
that
the
is after, so you compute that a quantity d of x comma x dash plus r minus, but for that you assume that you assume that is unexpected and then calculate this. How do you know whether that is unexpected or not? Like, do you do it for all?
Okay, so unexpected means, so there was a predicted instance and here's a true instance. If here is a certain request which is predicted, but then in a true instance, it does not appear. So this point doesn't exist. Let me, yeah, so like in this picture. So here this is what I predicted, it's just one request. And let's say this didn't appear. So in the true instance, this is not there.
Okay.
And in hindsight, after I've seen the true instance, I can see whether the prediction was correct or not, right?
Yeah, okay.
And I want to quantify this. I want to define this error measure here to put a number on this, how bad, how wrong was the prediction. And maybe let me emphasize this here. So this is something it's an error notion that I define, and I use this for analyzing an algorithm, but an algorithm does not know what the error of the instance is. Yeah?
Sure, you don't need to define specifically unexpected, because for the expected one, the distance is 0 anyway.
So indeed, so here I gave you only those interesting requests. I could also give you a full bipartite graph having all the requests, all the true and all the predicted requests. And for those requests that are actually true, correct, I put just an edge cost of 0, and my min cost edge cover would certainly take this edge cost. Yeah. So here I want to emphasize those that I actually need to cover, and the others don't cost anything. But it's very right. Yeah. Okay. So again. So this is something we just defined. Let's leave it aside for a moment. An algorithm just sees the prediction and wants to make use of this somehow. It doesn't know whether it's good or bad. I mean, somehow an algorithm would like to just trust the prediction and just follow it. But this is super bad. It can be very bad. If the prediction is correct, then it's exactly the right thing to do, right? Just do what compute the optimum tour on the prediction and just follow it. But this can be very, very wrong. So in our notion, this is not robust. Imagine the situation, the server is here, and the prediction says, far, far away, there is a request. If I follow the prediction in the sense of I do the optimal thing with respect to the prediction, I would immediately start traveling and go over there. But what if the true instance consists just of a single request just close to the origin? Then it's super, super bad, right? So we need to do something smarter. And what typically learning augmented algorithms do in some clever way, they combine offline and online algorithms. This is very hand-waving, and this needs some nice tricks and elegant solutions in between, but somehow we want to follow the prediction and have a good algorithm that uses these predictions. That would be an offline algorithm. And to be robust, we need to combine it somehow with an online algorithm. Now, such a combination in this TSP-like problem cannot flip forth and back too often, right? Because if the servers stand far away in different algorithms, I mean, I would have high switching cost. We can do with just one switch. Okay, so our general framework for an algorithm is this one here. Let me say we are given the prediction and we compute an optimum tour on the prediction. This is T hat. And ideally, we would like to follow this prediction. Yeah, and whenever an unexpected request appears, we make a detour in some smart way. As I just said, this is arbitrarily bad. So we need to delay this, or it is sufficient to just delay this step. And before we start doing this, follow the prediction, we run a black box online algorithm, take your favorite row competitive online algorithm for online TSP, and run this for a certain amount of time. And this amount of time depends on what's the cost of this optimal tour. So the cost of this optimal tour, let me denote this by C T hat. And let's pick some alpha. I talk about alpha in a second. It's some positive value. I follow an online algorithm for a certain amount of time such that I can return to the origin by time alpha times the cost of the predicted tour. Okay? This alpha is a confidence parameter. So we will see this later. Actually, we will see this here, how we use this. So for now, maybe ignore this. Let me already now show you the result or the statement that we can show. If we run a row competitive online algorithm in this first phase here, then we can show that, ignore the alphas for a moment, suppose there's no alpha. Then here we would have a row plus 1 robustness guarantee. So row is a guarantee of an online algorithm, and we have a slightly worse robustness guarantee, worse by an additional 1, which is not too bad. But the benefit is that in our error-dependent part, we can be much, much better. So if my error would be very small, again, forget this alpha, then here I have an optimum solution plus some term linear in the error. So if my error would be 0, I would be optimal. This is really cool. And if my error increases, then yeah, I have a guarantee of opt plus something increasing in the error. And at some point, the robustness guarantee kicks in, okay? So this is exactly this type of guarantee that we would like to have. And this alpha essentially is a confidence parameter. It plays, or you can play, weighting either this robustness guarantee or more the confidence into the correct prediction. So if you assume, or if you as an algorithm user believe that the prediction most likely will be quite good and you will end up in the minimum on this side, you choose here a very small value, of course, at the cost of having a larger robustness guarantee, and otherwise vice versa. Okay? So this is using this arrow that I just defined, and now let me show you how we can make use of this maybe a bit crazy arrow definition. Okay? And it's very natural and plugs in here very easily. So let's first talk about robustness. If the algorithm terminates in the first phase, where I run just a row competitive online algorithm, then I automatically will also be row competitive, right? That's easy. So now, what if I terminate in the second phase? That means that my first phase, remember there was a condition that I leave the first phase, so I have to be back to the origin at a time that depends on the total cost of the predicted tour. So let me call this is the cost of the predicted tour. So now I know if I was my row competitive algorithm was not done by time alpha times C hat, then I know that the optimum must be larger than this quantity. And this gives me a nice lower bound, and based on this, I can then analyze my tour. Okay? Now, more interesting is the error dependency, and this is, of course, where the error definition now comes in. So this is in 2 steps. First, I would like to bound the total cost of the predicted optimal tour. Now, given the predictions, I computed this optimal tour. I would like to relate this somehow to the optimum cost. And of course, there must come in now the error, right? Because the prediction might be off from the real tour. So let me show you what I would like to show. I would like to show that the cost of the predicted tour is at most opt plus 2 times some error. And actually, this is the error for the absent requests. And let me show you why this is true. So here's a wild picture. Color code, again, pink is a prediction and green are the true requests. Yeah, and you see that some requests, this is a correctly predicted request. This is a unexpected request. This is was predicted but is absent. So there are all kinds of options, okay? What I show you here in green, this is the optimal tour on the true instance. So this is my optimum. And I would like to bound, or I would like to say something about the total cost of the predicted tour. So somehow the optimum tour on these pink points. I don't draw this tour here. But I know that the total length of such a tour cannot be worse than taking this green tour and making detours, so the cheapest possible detour from the green tour to serve the pink requests. This is clearly an upper bound on the shortest length of a pink tour, right? But this is exactly what I have written here. What does it mean, the cheapest way of making a detour? In our graph here are these predicted requests, all these pink points on the left-hand side. And I computed the min cost cover, and this was my error gamma, this this yellow gamma. So this edge cost is exactly the cost for such a detour. And this way we automatically get this bound. So we now have a relation between the predicted tour and the optimum. And now we need to analyze how, what's the total length of our tour that we then travel. Again, if we end in phase 1, then we can directly bound our tour length by alpha times c hat, just by design. And then we could plug in this part. A bit more tricky, and here I don't show all details. A bit more tricky is the second phase. So here we follow the prediction, and whenever there's an unexpected request, we make a detour. This sounds very similar, right? So we follow a certain tour, make detours, and cheapest detours would be according to our error. We have to be a bit careful with which requests we have already served and not. So this gets a bit more technical, but we can show that our tour is not longer than 1 plus alpha times c hat plus 3 times the error for the unexpected requests. And then we plug everything together, we get our bound. Okay? So this is a black box algorithm, so that's the same result I just showed you, and now with the correct bracket actually. So this was what I just showed you. One can, of course, fine-tune this a bit better. So if we know what algorithm we use instead of this row competitive black box algorithm, then we can get a better result. So here, if we use a 2 competitive smart start algorithm, that's the best known algorithm for online TCP with some smart delay strategy. If one digs into this and is a bit more careful in switching from phase 1 to phase 2, then one can get a better robustness, a robustness factor of 2. Okay, and now, remember the best known online guarantee is 2. So here we only, by this trustness parameter, are off from that. Okay, and one can also generalize this to online dial write problems of the similar style. So here now, of course, we have to adjust our error measure, and also the algorithm gets slightly more involved, but it's the same pattern. And the error measure, that's the interesting thing, we have the same min cost edge cover. We just adjust the cost for the edges. No, because now we have to take these transportation requests into account. And if you care about running time, so what I talk about here, I assume that I can compute these offline tours optimally in polynomial time. If you don't like this, take your favorite approximation algorithm, and then of course this comes in the guarantee. Okay. Okay, so now we have this error measure. And it looks already a bit general, that's good. But let's look at this error measure again a bit more carefully. Let's question whether this is a good error measure. And it's not really clear what defines what is a good error measure. But one can look sometimes at particular instances which look very natural and then see a discrepancy. So one of such examples is this one. We have just one predicted request. It's wrong. The actual requests are all here, very close to each other. So if I think about my current error definition, then I would have all these detours, right? So in my bipartite graph, I would take the cost for each individual green point. But this is nonsense, right? If an algorithm gets such a prediction, and let's say time-wise they are also very close to each other, then I have to make one detour and then serve all these requests. So this is not a really bad instance. But my cover error would be super, super large. And this is what we don't want. We would like to have small errors to get tighter guarantees. Yeah, so our error dependency is stronger if the error actually is smaller. So, and here it's very natural to say, well, I just serve them in one tour. And this suggests in this bipartite graph picture to think about hyper edges. Yeah, so instead of serving each of these unexpected requests individually, I say, well, I cover all these requests within one tour, starting here at its release date, and then serving all of those and then coming back. And I don't want to write this cost for you now, but you can express this and precisely define the cost for an arbitrary hyperedge. Now I could look at the bipartite graph, look at all possible hyperedges, and compute a min-cost hyperedge cover. And this error is much, much smaller. Now, what apparently machine learning people like are configurable error measures. So here you could even say, well, I configure it by a parameter k, and k says my hyperedge can have size of at most k. Okay? Now, our hyperedge error is, and here's a little, maybe somewhat strange thing, we take this gamma k, so we parameterize the side for the unexpected requests, but for the predicted requests, we can even use the gamma infinity. So what does it mean? We don't bound how big the tours can be, the hyperedges can be. So this is stronger, so this error is smaller, this part here. However, this part I want to keep. So, I mean, if you don't like this, you can also put there k. I don't care. It will be only weaker, okay? But we can even use this. And now we can show similar results as I just showed you for online TSP. We can also show with respect to this error. However, and that's, did I put this here? Yeah, we can show this only for lambda 1. So somehow in the way our algorithm works, for our algorithm, we cannot use larger hyperedges in the error measure, because for us to bound the error by the unexpected requests, it should be larger. Because, so somehow one could say, well, for an online algorithm, it's much more difficult to handle the error that comes from the unexpected requests, right? Error that comes from prediction is maybe not so bad, but the unexpected request, this is really where the online flavor comes in, and this will stay to this problem. Okay, so we have this error notion, this hyperedge cover error, and we can use this also for other graph problems. I mentioned earlier this problem, so the online Steiner tree problem. So these points appear now one by one. There's no timing issue anymore, so it just, a request arrives, immediately connected. Also here we could say, well, suppose we are given all the nodes that will be terminals, they're marked in advance, we know them. And now we want to design an algorithm that is making use of this and has a good performance, a good error dependency. And here we define our hyperedge cover error this in a similar way. Again, we have a predicted request sequence and a true request sequence. And for each unexpected request, so a true request that was not predicted, we have this one type of error, and the other error is for the predicted absent requests. Again, we set up our bipartite graph, hypergraph, and now the cost function just changes. So now my cost function for this covering would be, what's the optimal Steiner tree for terminals in a certain subset on the left-hand side of the graph with the root x on the right-hand side. This is our covering. So the root x covers all these terminals. And then you put this in numbers and compute this. So this is our notion of error. And there has been previous work that looked at this and other network design problems, and Yossi and Detmalia, and they proposed a nice algorithm. And I will talk later a bit more about their error. So this metric error with outliers that I mentioned earlier, this has two parameters, delta and d, and their performance guarantee looks like this. So right now it's only important, so it depends on two parameters, one additive error and one multiplicative error. Yeah, and we come back to this in a moment. Let me only sketch how their algorithm looks like. It's a very nice, greedy algorithm that in a smart way then exploits the predictions. And so here I draw maybe think of this as a sequence of requests, and I color a request differently depending on how it is served. So a request, so in principle, we want to run the greedy algorithm. So always when a request comes, connect the cheapest way. This incurs cost, and you keep track of the cost. At some point, when your cost doubles, then you can afford, in these red parts, then you can afford to buy some predicted requests. Yeah, so you run greedy, you run your online algorithm, And if you have spent there enough cost, then you can afford to buy a good set of terminals. And what means a good set of terminals? Well, for the budget that you have, you buy the maximum number of terminals that you can connect with this budget. So it's kind of a price collecting Steiner tree problem. Okay? And yeah, so I don't want to show this here, but we now take this algorithm and analyze this with respect to our error measure. So the type of result that we get is that our algorithm is constant competitive plus some additional term. And this additional error dependency for the online Steiner tree problem looks like this, that we have here our k, lambda k, the hyper edge cover error with edges k, and a factor log k in front of this. And the robustness is guaranteed already by the results of Jossi et al. And so now this we can also do for the other problems. So here's a table for well, this routing problems I said before, but here are these network design problems. And the other guarantees we get of similar flavor. So a constant competitive ratio plus some term for the error. And so now a question would be, well, first of all, so what is nice is that, yeah, we have this general cover error or this framework of how we quantify the error. And the problem-specific change is then only the cost function for the edges or hyper edges. Okay? But somehow the big question is, how do we compare actually error measures? So right now, we come up with this error measure, and we can compare it, for example, to Jossi's and Debmalia's results, but it's complementary, right? We cannot say that ours is always smaller than the other one or vice versa. There will always be examples on both directions. Actually, let me show you one of those examples. So I mentioned earlier the number of wrong requests is an error measure, and there actually Mosley and Xu also showed a nice guarantee for a greedy algorithm, which is log eta times opt competitive, which is actually nice, which also nicely grows with the error. And in the worst case, it's log n as a competitive ratio, which is also the worst case for the online setting. And this error that I mentioned already, this metric error with outliers, you take a matching between some subset of points, a min-cost perfect matching, and those terminals that you don't consider in this matching, they count in a different measure. They're counted in the set of outliers, so you count how many outliers you have. So there come these two parameters from: the number of outliers, delta, and d, the min-cost matching. Okay, and they have this error measure. So now consider the following type of instance. We have just one correct prediction, and then there's another prediction which is not correct, but there's in an epsilon ball, there are many, many, many other true requests. So for network design problem, this is not a bad instance, right? You just connect, and these costs are not so much off from the true cost. So I would say this is actually a pretty good prediction, but if you look at the number of errors, I mean, it's huge, and the error bound of Mosley and Xu would be log n, like the online algorithm. So bad, or worst case, let's say. And also for the metric error with outliers, just by parity, I mean, you will have many outliers, roughly n outliers, and that's why also this guarantee will be log n, like in the online setting. Whereas in our hypergraph or hyper-edge cover measure, we get a constant plus this error term, but this is negligible. It's super small. Yeah, so in that sense, this is a tighter, finer, more fine-grained error. And now the question is, how do you compare errors? Is there a general framework for how what should error measures satisfy, what not? How do we decide what's the better measure? And now I wanted to spend more time on discussing this, but I won't have the time. So let me just briefly say, I personally think that error measures can be problem specific, so they should take the cost function into account. Otherwise, for certain problems, you will not be able to show any nice learning augmented results. So this is what I did here, and I wanted to show another example from the scheduling world. I will skip this and come to the end. Oops. So I mainly talked about this universal error measure, and I think it would be nice to formalize a bit better notions of error and discuss this a bit more in the community. Other open problems or other research directions would be to say, well, let's exploit these predictions also in other areas. So let's improve running time, let's use this in mechanism design, improve price of anarchy or something else. Let's look at dynamic algorithms. And this is already done, but the majority of work is so far in the online world. I talked here only about input predictions. One could also predict much less input. This is something I find interesting, how sparse, how little information are enough to improve the algorithms. And one could also say, well, machine learning tools, they also compute predictions for algorithmic actions. So how do we analyze those? And there are some first works. And I think it's important to actually integrate this black box prediction world and our learning augmented algorithms. So I would like to integrate this learning into algorithm design. So for example, for these graph problems, let's say we solve them in several rounds, like every day you have to solve the graph problem and learn over time from the instances that you've seen already. Okay, that's all I wanted to say. Thank you for your attention.
Time for just one question.